This is problem number 15M. It's on page 393 and it's in chapter 7. The modified I section shown in the figure below is to be made from extruded aluminum. Specify a suitable aluminum alloy if the beam is to carry a repeated load resulting in a bending moment of 275 Newton meters. And we haven't really talked about what would happen with a repeated load. I'll describe that in context of this problem, then we'll go through some slides to know what we should do. But anyway, so 275 Newton meters is the moment. Now, apparently that's the moment applied to this particular section. Now if you look at this section, you'll notice that the top flange is 40 millimeters wide, the bottom flange is 20 millimeters wide. So just intuitively, where do you think the centroid should end up? A little higher, yeah, a little closer to the top, right above center. That what, 60 millimeter height? So I went into Excel and just did the same things that I showed you how to do from chapter 6, and here's the results. The section, the centroid is almost 34 millimeters to the top, and if you're watching this on the video, all these problems will be available. Probably the spreadsheet will be available by the time you watch the video. So anyway, it's 33.86 millimeters or so from the bottom, and all I did is I broke it up into 3 parts like you've seen done before, so I won't belabor that. But one thing that's important here, especially when you get into chapter 7, is to remember what units we're dealing with. Yes, sir?
Can you turn that off, please?
Yeah, sure. Thank you, sorry, I forgot.
I have a question. Did you say that was around 34 meters from the bottom? Or 34
Millimeters
millimeters
from
from
the
the
bottom.
bottom? Oh, that's,
Which should make sense, right? Because the center of that figure is what, 30 millimeters? We expect it to be slightly above that? Because it's 50 at the web and each of the flanges are 5 thick. Does that make sense?
all right.
Okay. So I expect it to be slightly above. That's just the location of the centroid measured from the bottom. Okay. So there's our centroid. Here's the area moment of inertia. And you have to be really careful, like I said, with the units. What are the units of this area moment of inertia? I mean, that number means nothing, right? If I tell you I'm going to give you 1 billion, are you happy? 1 billion what? Femtoseconds? You know, I mean, what am I talking about? The dollars? Yeah, that's great. Of course, the rate at which I give it to you would be really important then, but, you know. So what units are these? Would be something to the 4th power, some length to the 4th power. We're working in millimeters in this, or I was. You'll notice we've got an area of 100 square millimeters, right? That would be that lower flange, the 20 by 5. And then here's the upper flange that was 40 by 5. Okay. So the area is obviously millimeters squared, the lengths are in millimeters, and so this must be millimeters to the 4th power. Okay? We have to be aware of that as we solve these problems, because you'll end up with a lot more unit conversion. So anyway, the equation we've learned so far is that the stress is MC over I. In fact, this would be the maximum stress, would be the maximum bending stress. And we know that bending stress is a normal stress, okay? It's not something that's along the surface that we imagine being cut. It's a stress that's coming out from that surface. And so you can see the surface that's experiencing stress. Your author drew it for you. It's this. Okay, and really we don't need those. This is all one solid beam by assumption, okay? So this is the surface that has little stress vectors coming off of it, right? Now, he didn't tell us whether the beam is bent up or bent down, so we don't know if the top or bottom is in tension or compression. We just know that there's a load everywhere. We also know that since the center of the height, the 30 millimeters, is about here, and so our centroid is up here somewhere. If there's 30 millimeters there to the bottom, then what we're really interested in, this centroid, that's the 34 or so millimeters, if I can round it off. Okay. But where would the highest stress be? Well, notice that the cross-section I, or the cross-section, has this area moment of inertia. It doesn't matter is it's not like this point has a different moment of inertia than this point, right? Or anywhere in between. This is just the section property. So where are we going to find the maximum stress? Well, we have to be careful. It's not going to be at the top of the beam. Why? Because the distance from the centroid to the top of the beam is less than the distance from the centroid to the bottom. So there's a different stress at the top than the bottom. Okay? In fact, really what we want is the distance to the bottom in order to get the actual maximum stress. Does that make sense? So you have to be kind of careful as you're going along. Anyway, so we know the magnitude of the moment. Okay, we know the distance to the bottom. In fact, that's the 34 or so millimeters. Okay, this Y bar here. So I'll write it in with a little more precision. And I'm going to be careful. 0.03. Let's see, how many did I take? I took 3, 8, 6, and I quit at that point. Now that's meters, okay? Because I want to make sure that my units are consistent. Now in the denominator, the number in the spreadsheet is 272,935.6, and you agreed with me that that was millimeters to the fourth. How would I convert that to meters to the fourth? What would you do? Divide by 1,000 4 times, right? Here's another way of writing that. There's 1 meter, if I can write a decent M, I'd be doing well, per 1,000 millimeters. But that's not enough. I need 4 of them. So let's raise this to the 4th power. Does that make sense? Does everybody see how the millimeters will cancel from this? I know units are one thing that all of my thermo classes struggle with, and I pound it into them anyway. I'll do the same thing with you guys. Units are really important. So the millimeters to the 4th power will cancel. What am I left with in the denominator in terms of units? Meters to the 4th power. Not meters, meters to the 4th power. Okay? Because this 4 acts on the 1 and the 1,000 the same way it acts on the meter and the millimeter. Okay? All right. So now our units are consistent. In fact, what would the units be? We'd have meters squared in the numerator as far as the length portion is concerned. Forgetting the newtons for a moment. Length squared in the numerator, length to the 4th in the denominator. So what would the units be?
Newtons per meter squared.
Newton per meter squared. A Newton per meter squared is a? Few people know it as a Pascal. A Newton per meter squared is a Pascal. It's a force per area. And so the units we have here are pascals. The number, notice I frequently talk about the units before I talk about the number. Important that you start thinking more about the units. I do that on purpose. A lot of times you guys will just type the number in your calculator, write it down, and away we go, right? Who cares about the units? Well, I care about the units, so I want you to as well. They're important. Anyway, this comes out to 3.4, well, approximately, 3.412 times 10 to the 7th, and you guys agreed that would be pascals. Okay? All right. Well, one of the things that they told us in the problem statement is that the load is a repeated load. You guys know what a repeated load is? What does that mean? Well, see, the way things fail depend on more than just the magnitude of the load. It depends on how the load's applied. And so if you take a material and you apply a load to it and then you remove that load and then you apply the load again and you remove it, or you change the direction of the load continuously, what you'll find is the material will fatigue. Fatigue is a very different phenomenon than just applying a load and the thing ultimately breaks. Okay? So a repeated load, the idea of it is that it is a fatigue type load. Now in this chapter there are some guidelines for the type of load and how you should deal with it. And by the way, this is a very simplified approach, but it's okay to begin. And so let's go, let me find the page number for you. I found it earlier today. I've got it in the slides for today as well. Here we go, page 368. You'll recognize this. Your author has given us several tables like this already. But it's just a recommendation for stress guidelines. So how much stress should you allow the material to experience versus the strength of the material? That's what this allows us to determine. Okay? So table 7-1, page 368, the recommendation is that if you have a repeated load, then the stress, the design stress that you should allow the material to experience should only be 1/8 of the ultimate strength of the material. What you'll find is that frequently should be always, the strength of a material, when you're, I don't know how to say this very well, I feel dumb talking about it because I can understand it, I just don't know how to describe it well. When you're looking at how materials fail, the strength in fatigue correlates better with the ultimate strength than it does with the yield strength. Does that make sense? Now, it's not a one-to-one comparison. There's a lot more to fatigue. I think that's why I'm struggling to talk about it. This is an extremely simplified way of looking at fatigue. But the point is that the strength of the material to resist fatigue depends more on its ultimate strength than it does its yield strength. So go to the back of your book. We're supposed to find an aluminum that will take this load. So go to the back of your book and let's see, the page I want is 718, table A18. And by the way, this number is 34 or so megapascals. A little more, but for right now, that's fine. Okay. So if we look, you can say, wow, well, pretty much any aluminum would take 34 megapascals. Yeah, but there's that safety factor or that fatigue factor. Back on page 368, we're only supposed to use 1/8 of the ultimate strength. Well, that makes things a little more difficult because that means we need to go and look at all these ultimate strengths, divide them all by 8, and then compare them to 34 megapascals. Does that make sense? I would much rather take the 8 and multiply it by the stress so that I could just go and compare. Does that make sense? So 34 or so times 8. When I did that, I got about 273 megapascals. So basically, if I take, here's what I did. I said the ultimate strength should be 8 times the design strength, just rearranging what was in the table. And so this comes out to about 273 megapascals. Well, now there are several aluminums that carry this load, but not all of them. In fact, the one that I chose was 6061 T6, which has an ultimate strength of 310 megapascals. You wouldn't have to. You could choose something with a higher strength. You could choose something with twice that strength if you want. It doesn't matter. The point is, this is the minimum recommendation. Okay? This is the minimum strength or ultimate strength that the material would have to have in order to resist this load. Does that make sense? Any questions on that? Okay. So to finish this off for the sake of the video, I chose 6061 T6, and it has an ultimate strength of 310 megapascals, so we should be able to take this load without too much trouble. Okay.